Live here. All right. So I think we are live in the IOQM problem solving. So the question paper is available in the chat. I'll just put it in the chat actually. If someone wants the question paper, and uh, let's see. So we have Arjun and Gunjan with me, and I think Raghunath is joining very shortly. We plan to solve the entire IOQM paper today, and Arjun said that we should not stop before we complete the entire paper. So let's see if we can do that. So Arjun, I think you are starting from the last one, right? Is that correct?
Yes,
So and Gunjan maybe so you can start from 25 or I don't know 2022. Okay. So the question paper is, I'll just give you guys a couple of minutes time to, think about the questions. And so here is so I gave the link to some other places. I'll just let everyone think a little bit about the questions. Just put the question in the question paper on the screen for a moment so that others can see it. Okay. So let me just shift the screen. So I'll just share this particular tab. Okay. So I think the question paper is now visible and everyone can see it. I'll just wait a little bit for others to try the paper and then we will get started and we will start solving the papers together. So So if you are not able to see the paper, if you are not able to see the paper, I will request you to go ahead and make sure that your um, the video is turned in the HD mode. Because if the video is not turned in the HD mode, then that would be a problem. You won't be able to see the video in the right mode. Okay, let's start with 30 then. And you have the access, right, to the Jamboard? Okay, so let's let's do that. Yeah. So I will go back to this and let's see. Yeah.
D of 2 is 2 because 2 has like two factors which are 1 comma 2. Then D of 3 is also 2 because 3 has factors 1 3. And then D of 4 is 3 because its factors are 1 2 3. Then D of 5 is 2, and so on. uh, Maybe some people and the question is asking us to consider this sum, uh, and it's asking us to determine when it is odd and when it is like even. That's essentially the question.
Right.
So our strategy for our question would be to characterize all n for which this is even, for which this is odd. For example, we will do some kind of characterization like if n has this special property, then it is odd, and if n has some other property, then it is even. And once we are able to find such a good enough characterization, then rest of the question would just be counting the number of such n for which it is odd. So the hard part of the question is to determine for which n is it odd and for which n it is even.
Right.
So let's start with the question. So first we'll do some analysis about this function d, what is exactly doing. Our first observation is that like we only care about the parity. For example, we only care about whether dm is odd or even. We don't care if it's equal to 1 or 3. For us, only the parity matters. And some of you might have noticed from small examples that, or might have conjectured from the small examples that d of m is even, oh sorry, odd, if and only if m is a perfect square. So I'll also prove this, but you might conjecture this during an exam by say like observation of small cases. So I'll present like two ways to prove this. One way is to just like pair the factors of m in pairs. For example, we create pairs like a comma b where a cross b is equal to m. Like you would have noticed something like this in school, where say you want to list the factors of 12, you do like this and so on. So essentially we are pairing like this. So if M is not a perfect square, then we create such pairs, and in each pair we have two distinct numbers. So the number of factors is even, and the reason is that we are pairing factors with each other. And since in each pair we have two, so the number of factors is two times the number of pairs. But when M is equal to say like t square, then one of the pair would be of the form t comma t, and in all other pairs you would have distinct numbers. So the number of factors this time will be odd because for other pairs we have like even number of factors, and for this t it creates an extra factor, so it's odd. Another way you can prove this is that you people might be knowing this. I'll go to the next Jamboard for clarity purpose. It might be little like we know that if m is equal to this thing, where p1 to pk are distinct primes and ei's are like positive integers or even non-negative, it doesn't matter. Then it is a well-known formula that dm is equal to this thing.
Right.
So from this, if we want dm to be even, all the ei should be even. Uh, oh, sorry. If you want dm to be odd, all the ei should be even, and hence m should be a perfect square. So essentially, what I've proven is this lemma. Our lemma is that dm is odd if and only if m is a perfect square, and we have also proven this lemma. So, given this lemma in mind, now we will proceed with the main question. So, let us define this quantity Fn as summation, this thing. The question is asking us to determine when Fn is odd and when Fn is even. So, first, let's start with an observation. From definition itself, uh, this thing should be clear. Like, this is literally how we define Fn. So, I'll go to the next Jamboard. And we also made an observation that when dm is even and when dm is odd, so I can make this claim claim, and our claim is that uh, uh, fn is congruent to f of n minus 1. Also, let me define this congruency sign. I'll say A is congruent to B if A comma B have same parity. Like if A comma B are both odd or both even. This is not a standard notation, but I'm defining this notation for this specific question to make our life easier. In general, we have to say A is congruent to B modulo something. Like we always have to write which mod is it, but I'm not writing mod to everywhere. Like, yeah,
Right.
why to explain? So now our claim is that Fn is congruent to this thing. Uh, uh, like it is this plus 1, like they have different parity if n is a perfect square, and fn and f of n minus 1 have the same parity uh, otherwise, like if n is not a perfect square. So let us observe a first few I hope this claim is clear to everyone. Maybe yeah, it's just literally direct from the lemma, and yeah. So now let us observe a few things. It should be pretty clear that f1 is equal to d1 is equal to like 1. Like also I'm just concerned about what parity is it. And from the above claim we see that f1 is also congruent, f2 is also congruent to 1 because f1 is congruent to 1 and 2 is not a perfect square. Then f3 is congruent to 1. But now f4 is congruent to 0 because f3 and f4 will have the opposite parity because d4 is odd, and like just remember the above claim. Then we get like f5 is like also 0, f6 is also 0. This continues till f8 is also 0. But now since 9 is a perfect square, so f9 is like congruent to 1. So essentially, if you observe how this sequence f1, I'll go to the next page for clarity. So if you observe how this sequence is behaving, f2, f3, and so on. Essentially, it's like 1, 1, 1, then modulo 2, 5 times 0, then 7 times 1. Uh, so essentially, what's happening is that it changes at square. For example, at f4 it is changing, then it remains same till f8. Then at f9 it will change and it remains same till f15. So now my main claim is the following. Main claim. Uh, suppose k square is less than equal to n k plus 1 square with where k is a positive integer. Like we pick the unique positive integer k for which n is between k square and k plus 1 square. Then fn is congruent to 1 if k odd, 0 if k even. So I'll tell the motivation behind this claim and then I'll tell the proof. So you people would have already observed that n is changing at squares. So it only matters between which two squares n is. Like among squares, like if two numbers a and b are between like same squares, there's no square number between them. Then they like have the same kind of f value. So you would have observed that essentially the points at where f changes this. And later you also observed between 1 and 4 it's 1, between 4 and 9 it's 0, between the 9 and 15 it's 1. So making this claim was quite natural. And you can easily prove this claim also. So there are two ways to prove this claim. One is you can just induct by using this claim, claim we have here, and the other is if you consider this sum like I'll go to the next page. The other proof of the claim is if you consider the sum like d1 till dn, you will see other than the perfect squares, all of the stuff like d2, d3, d5, etc. is d6 is just even. So you can just cancel them out and we get that summation I equal to 1 to n. Di is congruent to summation I is a perfect square, I less than equal to n, 1 less than equal to I less than equal to n di. The reason for this is just the fact that because at non-perfect squares, the values of d are even, so they can just be ignored when we are looking at parity. And from this equation, the previous claim should immediately be clear that the parity of Fn is just same as the number of perfect squares less than equal to n. So okay, this was our main claim that the parity of Fn is the same as the number of perfect square less than equal to it. So now we proceed to find the number of such Fn for which Fn is odd. Uh, we know like F1 is odd, still F3 is odd. Then we know from F9 to F15 is odd. Okay, first we want to look at all and less than equal to 2023, and we know, and it is quite easy to see that this thing. And also in the range 44 square to 45 square, all the mappings of f are even. So essentially we can ignore this range because in this range all the mappings of f are even. So essentially we just have to look the numbers till 1. We just have to look at this range. Okay, I'll go to the next page. Uh, so our search has reduced to this interval. See, reducing to this interval was nice because 2023 is not a perfect square, and then it might create some it might make our life harder. So we know that in this interval we have like three of them. Then in this interval, 9 comma like 1 2 3 are so from 1 to 3, f of n is odd. Then from 9 to 15, it's odd. Then from 25 to 35, it's odd. Here we have three numbers. Here we have seven numbers. Here we have 11 numbers. So this is a AP with the starting term 3 and common difference 4. And also now let's talk about the number of terms of this AP. So like uh, the term, so we are essentially looking at such intervals for which k is odd, and this and k odd, and we have 22 such intervals. So essentially we r is equal to this thing, r is equal to plus 11 plus 15 plus so on, still we get like 22 terms. um, I hope this is clear. Actually, after getting the main claim, you can just solve it in any way you want, but I'm solving it with this way because this was the first which came to my mind. So essentially, now we just have to compute this 3 plus 7 plus 11 plus so on till 22 terms. And I can write this as 4 plus 18 plus 12 till 22 terms minus 22. This is equal to 4 plus still 22 minus 22. This is equal to 4 times 22 times 23 by 2 minus 22. This is equal to 22 times 46 minus 22. This is equal to 22 times 45. And what is this thing equal to? This is 900 plus 90, which is 990. Am I right? Yeah, I guess so. So our R is equal to 990. But remember, this is not our final answer. In the question, let me go to the first slide and tell you people the original question. So the question asked us to find the sum of the digits of R, and we have found that the value of R is 990. So what is the sum of digits of 990? Just 18. So this is our final answer. 18 is the answer of question 30. If
Excellent.
anyone has any doubts in this question, I can try to clarify them.
Yeah, sure. That was great. Thank you for that. Let's move on to the. So the answer to the question number 30 is 18. That's great. So let's go ahead and work on problem number 5. Problem number 5. So I'll just put the problem here. It's a geometry problem. It's quite simple, I think. So
So sorry to interrupt. I also have one idea for 27 problem, but we
27.
can discuss it after this maybe.
Yeah, sure, sure, sure. We can do that. No problem. So here is the question number 5. This is, let me write it here. Okay, so this is, okay, one second. I think I have to give, uh, okay. Yeah, I think I have editing access now. Sorry about that. I didn't have editing access to this one. Okay, so this is question number 5 from the IOQM this year, and what it says is that in a triangle ABC, so let me draw a triangle. So ABC is a triangle. We have the midpoint of AC is E. Midpoint of AC is E. Midpoint of AB is F. The medians BE and CF, the medians BE and CF intersect at the point G. So G is basically the centroid. G is the centroid of the triangle. Now Y and Z are the midpoints of BE and CF. So maybe I can change the color. Y and Z. This is Y, this is Z. These are the midpoints of BE and CF. So we are joining YZ. The question is the triangle ABC, the area of triangle ABC is 480, sorry, it's 480. Area of triangle ABC is 480. So we want to find out the area of triangle GYZ, the area of triangle GYZ. That's what we want to figure out. Okay. So how do we go about this problem? Well, there are actually multiple ways of doing this, but one realization, one sort of observation is this, that if you have, so there are a bunch of parallel lines in this picture. So for example, EF is parallel, EF is parallel to BC, and it's half of BC. And oh, I think Gunjan is back. Yeah. And Y hits the midpoint. So if I extend YZ, let's call this T and let's call this R. So what can we say about TYZR? TYZR. So I think this one will be parallel to BC as well, isn't it? What do you think? TR will be parallel to BC. by the same midpoint theorem? Well, we have to check that because Z is the midpoint of,
Maybe y is not collinear with tz.
maybe Y is not collinear with TZ.
Tz.
Okay, that could be the case. Uh, okay, maybe that is true. Maybe Y is not uh, collinear with TZ. So, okay, maybe we can do something different then.
I have an idea of coordinate geometry, maybe.
Okay, yeah, we can use coordinate geometry here.
Example.
But I think we can also use the Shiva, like the Shiva's theorem, because we know
Hmm.
that. Okay, so maybe we do something different here. YR. Maybe, maybe this is not the. Someone is trying to enter. So, okay, so we have a kind of a. So what we have to do really is to compare the GYZ triangle with the main ABC triangle, right? That's the main contention. Maybe what we can do is we can probably join BZ and BZ, and we know that this is half and this is half. BZ, similar triangles. Okay, so maybe let's do it like this. Let's say this is x, then this is 2x, and this is 0.5x. Okay. This is 0.5x and this is 1.5x because that is the midpoint. And similarly, if this is y, oh, I cannot use y. Let's see. Uh, this is t, then this is 2t, then this is 0.5t, and this is 1.5t. Okay, so now I think we have it. See, what we have is that these two triangles are similar. See, what I just did is this, that, okay, let's forget about I'm trying to prove that I am trying to prove that YZ is parallel to FE. Okay, so how do I do it? I know that the centroid will divide BE into 2:1 ratio. I know that, right? So if this is T, then this is 2T. That is, if BG is 2t, then GE is T. GE is T. But that means YG is 0.5t because Y is the midpoint, right? Y is the midpoint of BE. Y is the midpoint of BE. So YG must be 0.5t. Otherwise, we cannot have 1.5t and 1.5t equal parts, right? So similarly, if similarly GZ is 0.5x. GZ is 0.5x. So that means that these two triangles, this triangle and this triangle, are similar to each other. That means GYZ is similar to GEF. And not only that, their side lengths are half. The side lengths of them are half, so their area is 1/4. If the side lengths are half, the area is 1/4. So triangle GYZ is 1/4 the area of triangle GEF. GEF is this one. Okay, so now the question is, what fraction of the entire triangle ABC is triangle GEF? Okay, so let's see how we can do that. So okay, so we can do this very easily actually. So let's see. We know that so the area of AFE is 1/4 of 480. AFE is 1/4 of 480. 480 is the entire triangle's area. So 1/4 of 480 is 120. So this is 120 because by midpoint theorem, this is half of this one. And these two triangles are similar. Okay. Okay, so yeah, we are done. So this is 120. And we know that this entire thing is, so if this, so look at this big triangle. This is the median. So this triangle BFE is 120. BFE is same as AFE. Both of those triangles have same area because EF is the median. And if you look at this little piece, this is 2:1. So the area, so this is this split piece's area is 1/3 of this big triangle. So triangle GFE is 1/3 of 120, which is 40. So GYZ, we know that it's 1/4 of GEF, which is 1/4 of 40, which is 10. So answer for this one is 10. Question number 5. Okay, so what is the next one that we will be doing? So a bunch of parallel lines and equal triangles and stuff like that. So I used a couple of things here, I think. I used the fact, at first I had to show that GYZ is similar to GEF. We used the fact that the centroid divides it into 2:1 ratio, and then we have 0.5 and 0.5 in each. So okay. I think the answer is 10, but some people are in the chat are saying 20. I don't know. In my opinion, it's 10. What do you think? Anyone of the panel? What do you think? Is there an opinion? So I'll just run through the proof one more time. So this is entire thing is 480. I hope I read it correctly. Yeah, it is 480. So this is 1/4 of 480, which is 120. So this is also 120. So if this is 120, okay, so if this is 120, then this is 1/3 of 120, which is 40, and this is 1/4 of 40, which is 10. 10 is the correct answer. 10 is the correct answer. I don't think that there is a problem with this. Okay, any other question that anyone in the panel wants to do?
Yeah.
Yeah, yeah, go ahead.
So can we try 27?
Let's try 27. Yeah, 27. I'll put the problem on the
Yeah.
board. Yeah, one sec.
Mm-hmm.
So,
Sir, also Gunjan was requesting the editing access of the
oh,
chat.
Gunjan is requesting the editing access.
Huh.
Gunjan, can you give the Gmail address that you're using?
I'm using the Cheenta email.
Are you logged in? Oh, okay. So,
Cheenta.newton@cheenta.com.
hold on. I'll just. So you are already given gunjan.agg27@gmail.com.
Oh,
You're already given that.
okay. I couldn't really log in with that
Oh,
account,
you are logged in with another one. Oh, got it.
I'll try once.
Yeah, yeah. So
Okay, that works.
I've given you access. Yeah. If you want, you can just. Okay. So that's great. Yeah. So let's go to the next question. This is 27, right? So
Yeah.
27. Let's copy this question and paste it in the. Okay. So this is in number 10. So I'm going to paste it here. Okay, so this looks like this. Okay, so
Yeah.
everyone think about this. Okay, and
Quadruple is said to be balanced. So we have A plus C equal to B plus D, right? And 1 is less than or equal to AB DC.
okay, let me first. I mean, for the viewers, I'll just read the question once. Okay,
Yeah.
because that would be a problem. So, a quadruple ABCD of distinct integers is said to be balanced if AC is equal A plus C is equal to B plus D. Okay, so maybe we can just give an example of a set of balanced integers between 1 and 20. So maybe 1 AB, right? 1, 3. So A, B, C, let's say 4, and D is 1. Okay, maybe they're distinct. So maybe D is 2. So make C. Okay, so this is so A B C D. So A maybe it's make C 4 and D 2. So A plus C is 4, B plus D is 2. So we say that A B C D 1 3 4 2. This quadruple is balanced. Okay. So let S be any set of quadruples ABCD, and where the cardinality of S is 4411. Find the least number of balanced quadruples in this particular set S.
So
So
basically, these are between 1 to 20, right?
these are between 1
So
to 20, yes.
so we will find the number of quadruples ABDC between such that the numbers are between 1 to 20 and they satisfy this relation.
Uh-huh.
So the number of just the number of quadruples will be 20 choose 4, is it not? Because like if you just choose 4 and they are already sorted,
Right,
so there is only one quadruple after choosing 4 elements.
right.
So for example, if I choose any 4, like let's say 1 3 7 17, so then A will be the least, so give it to 1 is given to A and 3 is given to B, 7 like is given to D, and 17 is given to DC, and that's the order.
Right.
For now, let's not worry about balanced quadruples, just the number of quadruples.
Okay.
So they will be 20 choose 4. And I think what is 20 choose 4? If we do, it is 20 into 19 into 18 into 17 by 4 factorial. 4 into 3 into 2 into 1.
Right. I just used a calculator. It says 483
48?
45. 4845.
4845.
Correct.
I see. So let's go back to the question.
Yeah.
The set S is also set of quadruples ABDC.
Right.
I actually it is ABCD, but I will change D and C because it's very easy to see in this way. So
Okay.
ABDC and ABCD are between 1 to 20,
Right.
and in this order. So such a set S has cardinality 4411.
Right.
So 4845 is the entire like maximum possible cardinality, and 4411 is the actual cardinality.
So they
So
maybe they did not take all the quadruples.
huh,
You
they
missed it.
missed some
They
quadruples, right?
missed some quadruples. Right. That's possible.
So now we should think optimistically. So they are asking for least number of balanced quadruples, which means I will leave out all the actual balanced quadruples away from
Right.
this in this 4485. I will leave out all the balanced quadruple, like maximum possible balanced quadruples possible,
So you're
so that what remains
yes.
will be my answer. Like that must be there. That many number must be there in the setters, right? So basically, the problem is just to find the number of balanced quadruple in this range.
Right.
So if I find this, then 4845 minus 4411 is equal to uh,
434. I think.
434. Yeah.
Yeah.
So these 434, I will leave out from the balanced number of balanced quadruples. So the remaining balanced quadruple must be there in the
Right.
set S. So let's find the number of balanced quadruples ABCD.
So we are trying to reduce the number of balanced quadruples.
Yeah.
So we want to maybe all the 44, 34 that we left out, we
Hmm.
discarded, are all of them balanced quadruples.
Yeah. 434 we left off for all balanced quadruples to be counting the least number
Right.
of that must be there in the set S. So having said that, the number of quadruples in such a way that the sum of these two is equal to sum of these two. And also we have that AB, DC. Like they are in the ascending order. Okay. So here we will do some caseworks. Little bit of casework and we will easily find a pattern to count. So the minimum number A will take us 1, which means the minimum number B will take us 2, and that D will take us 3, and C will take us 4. So the minimum sum of B plus D would be 5. And that is also the minimum sum of A plus C,
Right.
right?
Right.
So we will casework on the sum of B plus D and A plus C. That is the logic. So if this is the case, let's write out um, the pairs that satisfy. So the pairs that satisfy these are 1 4, 2 3. These are the possible pairs that sum up to 5. Then next comes 6. That is equal to b plus d equal to a plus c. So what are the pairs that satisfy? 1, 5, 2, 4. That only sum up to 6, right? Because 3 and 3 is not possible. No two, all of them are distinct. Next, for 7, it would be 1, 6, 2, 5, 3, 4. Then 8, I'm just collecting all possible pairs. 1, 7, 2, 6, 3, 5, 9, 1, 8, 2, 7, 3, 6, 10, 1, 9, 2, 8, 3, 7, 4, 6. So I'll just write out for 11 and we will observe a pattern here. So 1, 10, 2, 9, 3, 8, 4, 7, and 5, 6. Is that right? Okay. So 2, 9, 3, 8. Maybe why is the, I think I missed something. Oh, right, 4, 5. Yeah. 9 also comes with 4, 5. So the pattern is here that the possible, like from here, say if you take 9, the a plus c is 9, b plus d is 9. How will I find the number of quadruples? Isn't it just 4 choose 2? Out of the 4 pairs that are there, I just choose 2 and automatically it assigns to ABDC, values to ABDC. For example, I choose 1, 8 and 3, 6. Then this will define a quadruple. Why? Because the least value will go to A, and the next least will go to B, the next least will go to D, and the next least will go to C. So that A plus C equal to B plus D. Or I can also choose 1, 8 and 4, 5. Automatically it assigns value to ABDC. AB, sorry, this is not B. The next least is 4, next is 5, and next is 8. So like you just have to choose 2 pairs out of the 4 pairs that are present here. So 4 choose this number 9 generates 4 choose 2 quadruples. Like that, obviously different numbers generate different quadruples because the sum of the first and last elements are the defining cases. So the cases run up to 5 to maximum of I think 20, 19, 18 and 17. So the sum would be 37. So the 5 to 37 it will run. So if you see how the pattern that it goes off, let me erase this and write it in. Yeah, so these two, the first two goes to 2 choose 2. Only one quadruple they can give rise to. The next two gives rise to 3 choose 2 quadruples. The next two, 4 choose 2. And similarly, the next two is 5 choose 2. So we can easily see that there is a pattern that is going on here. So the similar pattern will not be continued because there is an upper bound also. We do not have only lower bound, we have upper bound of 20. So the pattern breaks at the when there is an involvement of the largest number, that is 1 and 20. So 1 and 20 happens to be occur for 21, right? So the same pattern goes till I think so basically odd even like that we go. 21 means so for 19 it starts from 118, 217 all the way till 910. So 20, it should also be the same 119, to 18 till 911. So number of pairs will be for both. Uh, how many pairs? Nine pairs. So 9 choose 2 for both. So yeah. So till this, it increases. Monotonically increases. 2 choose 2, 3 choose 2, 4 choose 2 till 9 choose 2. After 21, you will see something happen. So for 21, it is normal because 20 is valid thing, and it goes till I guess 11 and 10. Yeah, 10, 11. So for 22, it will be 1. 21 is not allowed, right? So we have to be careful here. Now we have 2 comma 20 till 10 comma 12. So here this counts to 10, whereas this counts to 9 only. So I mean, sorry, 10 choose 2. Sorry. Because two, like you choose any two pairs, it will form a quadruple. That's why 10 choose 2. Whereas this is 9 choose 2. And for 23, let's find. It will go from 320 till 11, 12. Yeah. And 24 will be 420 till 11, 13. So this correspond to how many 8 choose 2 pairs? Whereas this correspond to, oh sorry, this is not 8 choose 2. This should be 9 choose 2 only. This will be 7 plus 1, 8 choose 2. So 25 will be 520 till 11, 12, 13. So this will be 12 minus 4, 8 choose 2. So 26. So here the, okay. So this is 620 till 12, 14. Giving us how many pairs? 12 minus 5 will be 7 choose 2. So here there is a pattern, right? Clearly. Again. Now these two pairs up. These two pairs up. These two pairs up. And 8 choose 2, 8 choose 2. 7 choose 2, 7 choose 2. So this happens till the last sum is 37, right? So 30, let's do for 36. Like it is pairing up like even odd like that. So even means, so 36 we will work out. For 36, it starts with 20, right? So 16 and 20 and 17, 19. Yeah, so it will be 2 choose 2. And for 37 also, 17, 20, 18, 19, 2 choose 2. So they just pair up as we expected. So if we find the entire sum, we will get the number of quadruples. So basically, that will be 2 times of 2 choose 2 plus 3 choose 2 till I guess 9 choose 2. And then also we have from 9 choose 2 we go backwards. So I can basically count 4 times, right? Basically like 9 choose 2 is occurring 4 times. 1, 2, 3 here. And then yeah, 3 means like 19 and 20, 22 and 23. So 4 times it is occurring. By symmetry, you can easily see that every number occurs 4 times. Oops, sorry. Yeah. So we will write that 4 times of 9 choose 2 plus 8 choose 2 till 2 choose 2. But we missed one number. I think that should be 10 choose 2. I think we counted everything else. Now let's use the hockey stick identity, which tells that R choose R plus 1 choose R plus 2 choose till n choose R is equal to n plus 1 choose R plus 1. So this is 10 choose 3 plus 10 choose 2 will be 45. So 10 choose 3 will be uh, 10 into 9 into 8 by 3 into 2. 3 threes are 9, 4 twos are 8, 12, 120 into 4 plus 45. So 0, 4 twos are 8, 4 plus 45. So 5, 2, 525. So we get 525 quadruples ABDC.
Right.
So if I optimistically think and leave all the 434 that I'm leaving as my balanced quadruples, then the remaining quadruples will be 525. So the answer will be 525 minus 525 minus, sorry, I missed that number, 434.
So 91.
Yeah,
So it seems
should be 91.
it's pretty.
So at least 91 will be there.
Yeah, it's pretty awesome actually because you have to use some quite detailed analysis to do this. And
Yeah.
I wonder if there is like a
I think the way to count is important here. Like we just find the number of pairs. Like for 9, we just find the number of pairs and just choose 2 to generate the quadruple.
right,
So we just use that way to find the number of quadruples.
right,
Alright.
awesome. Okay, so I think Gunjan, do you want to present something?
Also, one thing
Yeah.
I want to mention another way of counting the quadruples. So ABDC. So this time the way we counted was we were counting ABDC by looking at the sum of A plus C equal to B plus D. But another way we can do is it by we fix the difference of C and A. Suppose we fix the difference of C and A as S. Then the number of possible values of B and D is S floor of S by 2. Uh, Actually, I don't know why I'm unable to write.
I think if you reload, sometimes it's happening. So I just reloaded, and then now I can write.
Okay, so I'll go on Jamboard 15. So so we just a second.
Yeah.
So we wanted to count A, B, D, C like this. And suppose we fix C minus A equal to say S. Okay, so let's look at how many possible choices B and D can take between A and C. So we know this thing. So B has S by 2 choices, floor of S by 2 choices. For example, say if C is equal to A plus 4, then B can either be, wait a second. Uh, oh, sorry, it's S minus 1 by 2. So then B can be A plus 1. And if C is equal to A plus 5, then B can be A plus 1 or A plus 2. Uh, okay, so now we if we count the number of possible solutions to A plus C minus A equal to S, where 1 less than equal to A C is less than equal to 20, we get the number of such solutions is 20 minus S because A can take these many values.
Right.
So our summation just becomes S uh, like uh, S equal to what can be the difference of A and C. It can be between 1 and 19, 20 minus S into S minus 1 by 2. And this is an alternate way to compute that thing.
Okay. I see. We have to check if the answer is coming up to be the same thing. Maybe it's not. I don't know. Okay. Anyway, so that's pretty nice. What about Gunjan? Do you want to present something, or do you have? Yeah.
Um, 29.
29. Okay, let's go to the. So whenever you guys are changing Jamboard, just give me a heads up because I'm sharing the screen so others will be able to see it as well. Yeah. So yeah, I'm in the 29th one actually. Yeah. So let me just put the question on the board. If that's so problem number 29. So let's see. I'll just upload the photo here. This is the one. Oh, some error is all occurring. I don't know why.
I've pasted it in the chat.
Would it would a copy paste? Oh, I think you just pasted it. Yeah. So just for the sake of the viewers and for myself, I want to understand. So a positive integer n is called beautiful. Okay. So a positive integer n is called beautiful if n can be written in one and only one way as sum of k numbers and product of k numbers. So where all the k numbers are in an order. For example, 6 is beautiful because 6 is 3 times 2 times 1, and it's also equal to 3 times 2 times 1, and 3 plus 2 plus 1. So you can write 6 um, as only one way, like um, 6 3 times 2 times 1 and 3 plus 2 plus 1. You cannot write 6 in two different ways. So 8 is not beautiful. They have given an example because 8 can be written as sum of four numbers and product of four numbers, and sum of five numbers and product of five numbers. So you have to be careful. You can use one over and over again. So the uniqueness is lost. Find the largest beautiful number less than 100. That's the question. So let's see what Gunjan has to offer.
So if we kind of look at the number just before 100, that's 99.
Mhm.
We can write 99 as 3 times 3 times 11. Now, one way to write 99 will be 3 times 33 times some, like a lot of ones. And the other way could be 9 times 11 times a lot of ones. And since we have like no restriction of the number of ones we can use, we can make sure that if these are k ones, then this equals 99 equals 3 plus 33 plus 1 times k, applying k equal 63.
Right,
So 99 can be written as 3 times 33 times 163 times, and it's the same as 3 plus 33 plus 163 times.
right,
And we could also write it like this, which is 9 plus 11 plus 79 times 1. So it's not really unique. So 99 is definitely not the number, the largest beautiful number, less than 100. So I'm moving to slide 17. And so my claim would be that any beautiful number would be of the form p times q, where p and q are primes. So I'll move to the next slide.
next slide. Okay. So yeah, that would be very nice if people just mention that they're going to the next slide, because then I can change it.
Um, yeah, because say a number n is just a prime, then if we write it as a product of numbers, it has to be p times a number of ones. And if we write it as sum of p plus 1, that obviously exceeds this. So this can't be. And if n is maybe p times q times a number r, not necessarily a prime, but p and q times, then we can write it as p times qr times pqr minus p minus r, like 1 is to this. And also q times pr times 1 is to pqr minus pr. This definitely equals p plus qr plus pqr plus p minus qr. And same with this. So this is not beautiful. But if you look at this, and we have to write it as a sum of a lot of numbers,
Right.
then we have basically two choices. Either we separate p and q, so it's p times q times a bunch of ones, or we keep it as pq and because we're adding one of q times to pq. So that doesn't work. But if you look at this and we multiply one a bunch of times, so this is pq, then we notice that and this is p plus q plus those ones. We notice that the number of ones is pq minus p minus q. And this is actually fixed because if we increase ones, then the sum increases, and if we decrease ones, then this sum decreases. So a number of the form pq is definitely beautiful. So we just have to look at the largest number, which is less than 100 and it's from PQ. So it's not 99. It's not 98 because it's 2 times 7 square.
Right.
It's not 97 because that's a prime. It's not 96 because that's 2 times 3 times 16. And it is 95 because that's just 5 times 90. So 95 is the largest beautiful number before 100.
So 95 has to be product of two
Yeah.
prime numbers. Okay.
Yeah.
Yeah, that's pretty nice. It's a very nice argument. Okay, okay. I think this is right. If no one has any objection, we can move to the next one. Arjun, do you want to take your turn?
Uh, yes, I would like to present. Actually, maybe someone else can present. I'm just in between 28. I'm just, yeah.
You're finishing up 28. Okay.
Yeah, then we will discuss 28. Like I also have some like I also started with 28. I don't know.
Oh, okay, okay. So we can start 28 then. Fine. Let's see. Let's look at 28. So I don't know. This is not allowing me to upload photographs.
Also, can we do it on a new Jamboard? Because I guess it will take more than 3 pages for sure.
New Jamboard. You want me to start another Jamboard, or we can just delete the existing things?
Okay.
What do you think?
Yeah, that's fine. I did not know that's a feature.
How many? Okay, so only 20 slides are allowed
Yes.
in Jamboard. Oh, I see. So yeah, I just deleted some of the initial ones. Okay. So okay, I'm now in the number 11, and the question is here. Yeah.
Yeah.
So on each side, okay, let's see. let me draw it on the picture maybe. On each side of an equilateral triangle with a side of length of n units. So if we have an equilateral triangle like this, side length of n units, where n is an integer, consider n minus 1 points that divide the side into n equal segments. So I'll just do it for 4, n
Yeah.
equals to 4. So we have 3 points which divide it into 4 equal segments. Okay, so it's here. Now, through these points, draw lines parallel to the sides of the triangle. So, like this. So, draw lines parallel to the sides of the triangle. So, I think if we do it correctly, then it will pass through the intersection points.
Oh, okay, okay.
Here we go. So, draw the lines parallel, obtaining a net of equilateral triangles with side length 1 unit on each of the vertices of the small triangles. Place a coin head up. So vertices of the small triangle, you place a coin like this, that's heading up. Okay, so two coins are said to be adjacent if the distance between them is 1 unit. So a move consists of flipping over any three mutually adjacent points. So we have adjacent points like this. So you can easily check that we have a.
I think on the vertices, do we have?
So on each vertex of these small triangles, so the vertices of the main
Hmm.
triangle are also small triangle vertices of the small triangle, right?
Yeah.
So that should be there. A move consists of flipping over any three mutually adjacent points. So you have any three, you can flip over these three maybe. It's possible. Uh, Two points are said to be adjacent. Any three mutually adjacent points. So you take. So you have to have. So you cannot be like this because these two are not adjacent, right? You have to.
Yeah.
You have to flip the vertices of a single small triangle.
Triangle.
Okay. So find the number of values of n for which it is possible to turn all coins tail after a finite number of moves. So if you flip these three, maybe so you start with heads. You start with heads. If you flip this three, then all of them become tails, right?
Hmm. Yeah.
But then if you flip these three, then two of these tails will become heads and this head will become tail. So something like that can happen actually. So now the question is, we have to find the number of values of n for which it is possible to turn all the coins tail after finitely many moves. So of course it is possible for n equals to 1. It's trivially possible for n equals to 1. You just turn it by once and you are done.
Hmm.
Is it possible for n equals to 2? Well, let's see.
Let's see.
You have head, 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 head. In move 2, let's say you can choose any one of them. Maybe you choose the, so you choose like this. This one becomes tails.
Yeah.
Then in move 3, this one, these two become tails. This one becomes head. And move 4, this one become tail. These two become.
Oh yeah. Now we can flip the middle triangle.
That's exactly true. This one become tails and this one become head. And now if we flip the middle triangle, we are done. So for n equal to 1, it works. N equal to 2, it works. Will it work for any triangle? Maybe it works for n equal to 3. I'll be just back from the washroom.
Mm.
Okay, so
Sir, can I present the solution?
yeah, go ahead.
Uh, uh, so, uh, uh, so for n equal to 3, it actually fails. And what we will, so the answer is that if n is congruent to 1 or 2 mod 4, I'll just write that. If n is congruent to 1 or 2 mod 4, then it works, and else it fails.
Okay.
And so we will prove this. And actually, this is quite a hard question. I think this is easily level in my opinion. But either way, let's proceed to the solution.
So wait,
Uh,
is the answer not a finite number?
I meant that like if n is 1 or 2 mod 4, then it can be done in finite number of steps, and if n is 3, and it's only talking about n less than equal to 100, so the answer becomes 50.
N less than equal to 100. Oh, I see. It starts with 100. I see.
So the solution proceeds in two steps. First, we will show that it is possible for n congruent to 1 and 2 mod 4. Then it fails for n congruent to that n for 3 or 0 mod 4. So the a few motivation behind this could be like I found that 1 comma 2 work and 3 fails, and I and like and even for I was not able to find a construction. So it was like tempting to conjecture that mod 4 is playing somewhere here or there. But we proceed to the solution. So first we prove that if n is congruent to 1 or 2 mod 4, then it works. And the way we will do it is by induction. So essentially, we will prove that if we can do it for a triangle with side length n, then we can do it for a triangle with side length n plus 4. And since we know that we can easily do it for 1 and for 2, like as sir just presented a way for 2, then we can do it for everything. So our approach for this question would be to like choose a set of triangles such that if we pick any vertex, then the number of triangles like in which it is a vertex is odd. And if we are able to pick such a set of triangles, then we are done. So I'm on slide number 12 and I'll try to write this more formally. So we'll pick T, a set of triangles. What the problem is equivalent to? We want to determine if we can flip a set T of triangles. Also, another observation, it is just stupid to act on a triangle twice, because if you suppose first flip three vertices and then flip them back again, then it's like you are just yeah, it's just the opposite of it. Just like you first flip it to head and then you again flip it to head, whatever. So I'll write S be a set of triangle, and for all vertices V, the number of triangles in S for which V is a vertex should be odd. So this is the equivalent transformation of the problem, because as I mentioned, it is stupid to flip a triangle twice. So every triangle either gets flipped once or zero times. So let S denote the set of triangles which will get flipped one times, and we want to choose S so that uh, the number of for like what the condition I've written for each vertex, the number of adjacent triangles in S is odd. So let's move to our induction. So what I will do is that suppose we can do it for a triangle with side length k. I'll prove that we can also do it for a side length of triangle k plus 4. So let us do that. So first I will tell you how to go from 1 to 5. For example, how does doing it for 1 translate it for 5, and the pattern wouldn't be hard to notice. So this is a 1 cross 1 triangle, and for this we just flip this triangle and we are done. And now we have to draw 5 cross 5 triangle. Uh, if possible, can someone who is fast in drawing can draw 5 cross 5 grid, because
Let me draw that. Yeah. So we have a triangle. Let's draw the one, two, three, four. One, two, three, four. One, two. Oh, sorry. One, two, three, four. And let's draw this. Yeah. Let's draw this. Yeah.
Also, another thing I would like to mention is that some people might be wondering what's the motivation behind this induction and all. So we have already conjectured that the answer is based on what is n modulo 4, and a very common technique for this could be to prove if n works, then so does n plus 4. So that's not very uncommon. Like it's quite common and intuitive. Either way. So first we suppose we have started from this one triangle. If I put a tick in a triangle, that means I've included it in the set S. Okay. And I want to do it for 5 cross 5. So how the essentially in general, when we are going from n to n plus 4, first we will have a n cross n triangle which is sort of done, and then we will have kind of a n plus 4 triangle for which we have like 4 extra rows which we need to cover, 4 extra rows of vertices. For example, this tick covers these 3 vertices. Now we have all these leftover vertices which we need to cover, like all these. So let's see which all triangle we want to include in the set S. So the set of triangles you will include in the set S are, I will put like this type of dot in there. Okay, I'll use some other colors so that it is more clearer. Okay, maybe that color. Yeah. So we will pick this triangle in our set as, this triangle in our set as, this triangle, this triangle, this triangle, this triangle. First, let me draw the construction. Later, I'll also tell you all about the notation and stuff. This triangle, this triangle, this triangle. And this triangle was originally there itself. And now in this construction, it's not very hard to observe that everything for each vertex, the number of blue triangles in which the number of red triangles in which it is in it is odd. So First, I will tell why the factor coded is 2. So essentially, we have covered all the above rows and we are only careful about the below rows. So let's look at the most bottommost row. You can see like for each vertex, it is in an odd number of triangles. Similarly, you can look at for this row, then for this row, then for the fourth row. Uh, we might, I mean, what more can I say about this? Like, this is literally how we are doing it. Uh, and now one question pops up is what is the motivation behind this construction? How in the world do we wonder that we will color this set of like triangles? So one thing is we want to have some sort of symmetry, like we don't want to look for very random patterns. Like we know the pattern we are looking should work for any set of four rows which look like uh, such a thing where a big triangle, where from a big triangle we cut a small triangle. So we want something that works for everything. uh, and then we like try to cover the bottommost row first, then we try to cover the second last row, then this row and this row, so this naturally pops up. Similarly, we can do this for a 6 cross 6 triangle. uh, uh, if possible, I'm moving to the next slide. Can someone please draw 6 cross 6 triangle or just copy paste it from the Google?
I'll draw it, no problem. I'm having trouble to copy paste stuff, so I'll just draw it. So one, two, three, four, five. One, two, three, four, five. One, two, three. Okay, so by the way, those of you were thinking that the old PRMO style problems will be back, they are sorely mistaken. This is nothing like that. Right. So anyway,
So yeah, now essentially what I will trying to do here is that demonstrate how we can go from 2 to 6, and it will be exactly how we went from 1 to 5. Uh, so this is a 2 cross 2 triangle, and the way we did for this was this. The way we did for this was we chose all these triangles, and similarly for the 6 cross 6 we'll chose all these triangles. So essentially, these vertices are now covered, and we want to cover the vertices in all the bottom rows. So we follow exactly the same pattern. First, in the bottom row triangles, we literally just pick up everything. Then in the above row, we pick up kind of alternately, and then in the next thing, the way we pick is a kind of a like we literally pick everything other than the two corners. Uh, and in general, what you do is whenever you go from n to n plus 4, you focus on the bottom three rows of triangles. Remember, I'm talking about the rows of triangles and not the rows of vertices. And in the bottommost row, you pick up literally all triangles. Like in this row, you pick up literally all of them. All of them. In this row, you pick up alternately, and in this, you pick all but two. Now, a good question you people a good and hard question you people might ask is why does all the vertices have an uh, odd number of triangles adjacent to them? So first observation is that the vertices of the n cross n triangle, which is this triangle, are already like covered, and no triangle in this red set is adjacent to this, so we don't have to worry about them. So our only worry are these vertices in the last four rows, and you can just observe this by structure. It's not easy, but you can see how the bottom row is covered, how the second bottom row is covered, and how the third row is covered, and how the fourth row is covered. It might be hard to give a formal proof, but with some observation, it might not be hard to see that everything is covered. Like you first see the bottom row is covered, then the second bottom row of vertices, then the third row, and then the fourth. And undoubtedly, this is a hard question, so the explanation and the stuff you have to notice will also be quite hard. So now we have I hope it is clear that how we can go from n to n plus 4, that how a construction of n plus 4 can lead us to a construction of n plus 4, how construction of n leads to a construction of n plus 4. uh, if I like misexplained it somewhere, or had I been not clear anywhere, I could try to clarify it.
Yeah, yeah. Basically, so in this pattern, you are flipping the triangles, right? The dotted triangles are flipped triangles.
Yeah, yeah, dotted
So
triangles are getting flipped.
flipped, and the entire thing will turn into tails now for n plus 4. Yeah. Okay.
uh, So if any one in the panel feels anything was unclear, I can try to like explain it for the audience more.
Yeah, basically, like a dot should be surrounded, like the black coin, the coin should be surrounded by odd number of dots, right? And that is
Precisely.
happening in this pattern. That is the thing, because it has to be flipped odd number of times to make it flipped from heads to tails.
Yeah.
Yeah, yeah, that sounds good. Yeah, you can go ahead, man.
So now we proceed to the second part of the question, which is to like prove that for n congruent to 3 and 0 mod 4, we cannot do such a curling. So I'm on Jamboard 15. Can someone just draw, copy paste any triangle of any side length?
Any triangle of any cycle,
Uh, yeah.
like a 3 cross 3 triangle maybe.
Maybe a 4 cross 4 to make the pattern more visible, I guess.
Okay, 4 cross 4. Okay.
So I'll tell you what I'll be doing. I'll be curling all the vertices in three colors, so that in each triangle I have one vertex of each color. I repeat, what I'll be doing is I'll color vertices of this big grid in three colors, so that in each triangle I have one vertex of each color. Yeah. So I'll use three colors. So I'll color this red, I colored this red, I colored this red, I colored this red, and I colored this red. So this is for the color red. And now
I
I'll,
think the page should be next page, the presenting page.
huh?
Uh, like the 15th page should be presented, right?
Oh yeah, yeah, yeah.
Sorry.
Yeah.
Okay, yeah. Here you go.
Mm, so okay. So this is how we are curling. And you people might notice that in each triangle, I have exactly one vertex of color red, one vertex of color blue, and one vertex of color yellow. Uh, Now, intuitively, it might not be very hard for you people to realize how the curling is being done and why everything is true. But for just for the sake of like formality, I'll explain more formally how I'm curling. So I consider this as a in the Cartesian plane, and I consider this thing as the x-axis and this thing as the y-axis. Maybe you can consider this thing at the z-axis. So this is like barycentric coordinate, and it might be little hard. So like this is barycentric coordinate stuff, and the other question is hard. So essentially, if I were to denote this point is 0 0 4, because the x-axis is moving 0 units, y-axis is moving 0 units, and z-axis is moving 4 units. And this point would then be x-axis moved 1 unit, y-axis has moved. This is how the points are. And then this point would be x-axis 1 2 1. Is it clear how the points are being marked with a triple xyz?
Yeah,
Like,
it is the magnitude of movement of the axes.
yeah, precisely. I don't know if there is any easier way to explain this. If anyone in the panel thinks there is an easier way, then please do this because it is important for the like understanding.
I think this is great. Yeah.
Okay, so if it is clear enough, then it's great. Okay. And another additional condition must be that x plus y plus z is equal to n. Here our n is equal to 4. Now you people might question why is x plus y plus z is equal to n, why we can do all this stuff so nicely. But this is all barycentric coordinates and you people can trust me for this, I guess. Maybe if you want to know more about this, I don't think you don't. Yeah, this is like the basics of barycentric coordinates. I don't know what more to say. Uh, okay, I'll give a small proof. So suppose you have a equilateral triangle, then you know that for any point P inside it, the sum of distances to the vertices is constant. You might know this property, and this is essentially why x plus y plus z is equal to n. Essentially, x is the distance of for each point P. Its x coordinate is it's the distance to this side, y coordinate is distance to this side, and z coordinate is distance to this side. Yeah, either way. So the points for which x minus y is congruent to 0 are colored red, for which x minus y is congruent to 1 are colored yellow, and for which x minus y is congruent to 2 are colored like blue. I think you all can notice this, that how is this being colored.
Right.
Uh, and from this more formal definition, it is quite easy to, not quite easy, but that in any triangle we have exactly one blue, one red, and one yellow vertex. So now comes the next observation. So we know any any triangle flip will flip exactly one red, exactly one blue, and exactly one yellow. So let R denote the number of red vertices, blue denote number of blue vertices, and Y denote number of yellow vertices. My claim is that RBW must have the same parity for such a thing to work. And the proof is suppose we want all the eventually suppose we want all the red vertices to be tails, then the number of triangles flips should be like say r is in okay for in this current figure what is r, our r is equal to 5, right? So the number of triangles flip must have the same parity as 5. uh, okay, I'll just mm, if I try to prove this formally, it might be a very big proof, but I think intuitively people might be able to see that in order for all red vertices to flip exactly once, we need to have the number of triangles flipped should be same as the parity of R. Maybe someone in the panel can explain that more clearly because I don't know exactly what are the right words to say here.
No, I think this is. So yeah. So sorry. What did you say?
I was saying that number of triangles flips for all red vertices to eventually become tails should be same as the parity of R. For example, it can't be like red vertices are 5 but the number of triangles flips are 6.
I see. Yeah.
I don't know exactly how to prove this in the most simplest way. So if someone can find the most simplest proof, then maybe he can proceed or something.
Yeah. We can proceed. I think. I mean, you can just put the claim and proceed.
Yeah, so this is the claim. Okay, I'll just write the claim once formally. It is quite easy to prove, and you people can think about it a little yourself. For all red vertices to flip uh, once exactly, uh, the number of triangles, like the
So I think
like
the
the
next page,
oh, I'm on the next
the
page. The number
yeah,
of triangle the number of triangle flips must have same parity as R. Okay. And if you want a more formal proof, I can consider this summation if we where V is red, and our FV is equal to 0 if V is head, and 1 if V is tails. And at each time I increase this summation by exactly 1. Like this parity of this summation changes, and at the end of the day, the parity of this summation should be R. So the number of flips should have same parity as R. Yeah, I think this is a quite simple enough proof. So I hope that number of triangle flips has same parity as all of R, B and yellow. So all of R, B and yellow must have the same parity. Is this claim clear? For if I can if I have a for a particular n, if I can flip the triangles in a way so that everything gets flipped exactly once, then the number of red vertices, number of blue vertices, number of yellow vertices must have the same parity. Is this claim clear to everyone? I guess it is. Also, I'm on page 17.
Okay.
So, is this claim clear to everyone, or
Yes, yes.
what
So basically, like to change the parity of that coin, you just have to flip that red coins as the number of total triangle flips, which is also the same parity as B and Y.
yeah, precisely.
Otherwise, one of the blue coins, if that is not done, then one of the blue coins will still be head, like that will happen.
So I'm on Jamboard number 15, where oh yeah 15, where I have this thing. So here let's just count. We have R equal to 5, B is equal to B is also 5, and our yellow is just a second. Did I mess up somewhere? Uh, Wait a second. Is there something like this? Uh, uh, just wait a second. So we have reached till this claim.
Okay. Yeah, take your time. There is no rush. I think this is a very tough problem.
Sir, could you please draw 3 by 3 triangle on page 17?
Yeah,
Yeah. Uh,
3 by 3 triangle. That's right. So go to 17 first. Yeah.
yeah. So I'll color this the similar way I did the previous time. This is red. This is red. This is red. This is red. Also, the way I'm coloring is just the intuition. The way you are like taking some sort of these. I'm traveling through these rhombus of sidelines, root 3 and stuff. That's the intuitive way I'm coloring. Yeah, so in this case, one might be able to see that, just a second, that R is equal to 4, uh, blue is equal to 3 and yellow is equal to 3. So in this case, it is not possible because RB and Y don't have the same parity. So essentially, what we have to do is that for each end, we have to determine if RB and W have the same parity. And to be honest, I will also have to calculate this, but we have reached till here. Um, uh, Also, I'm sorry, I previously said a wrong thing. The fact that n equal to 4 fails, actually n equal to 4 indeed works, and I will show construction for that.
Okay, okay.
So could you, do we have a 4 cross 4 triangle anywhere, or should we do it on page 18?
I'm doing on page 18.
So
So,
essentially, now that we have a construction for n equal to 4, we have constructions for all multiples of 4, because as I said, we can go from n to n plus 4, and we can go from 4 to 8 to 12 to 16 to 28 to 24 and so on. In a hurry, I by mistake missed n equal to 4. I'm sorry for that.
yeah, no problem. Just a second. So, wait. So this is, so I'm in page 18 now. And in page 18, let's draw one, two, three, four, five, six, seven, eight, nine. Right. Okay.
Yeah. So the construction is like you simply choose all the triangles other than the middle one. You just ignore this middle triangle and you simply choose everything else. Like you choose everything else other than the middle one. And it is not easy to see just by like direct stuff that this works. Okay, another nice question you people might ask: how can we see so quickly that every vertex is adjacent to like uh, an odd number of green triangles? And the point is, this figure is symmetrical. So if you do it for this vertex, then these two vertex are automatically done. Similarly, if you do it for this vertex, then all these 6 vertex are automatically done. So I was just telling you people a way to verify quickly symmetry. This is not much related to what we're talking about. So yes, what we have proven is that if n is congruent to 1, 2, or 4 mod 4, then it works.
Mm-hmm.
What we are left to prove is that for n congruent to 3, it fails. And for that, we have already developed our R, B, and W curling stuff. So what is left is that we just have to prove R, B, and W don't have the same parity. And let me try to find a good way to do that. I have not yet found one yet. I'll try to find the simplest.
Okay.
Uh, So till what I've done is it clear. So essentially, I'll repeat it. I've proven that if n is 1, 2, or 0 mod 4, then n works. And if n is now what I'm left to prove is that if n is congruent to 3 mod 4, it fails. And for failing, I have reduced it to proving that if RBW have essentially for it to work, let's go by contradiction. Suppose for n congruent to 3 mod 4 it works, then RBW must have the same parity and we'll find a contradiction by computing RBW. So we have to compute RBW for n congruent to 3 mod 4. For that, it might be helpful to go on page 17 where we have a 3 cross 3
But
triangle.
if it's 0 mod 4, if that works,
Yeah, it works.
if that works, then isn't the answer directly 100? Like, so we are supposed to find
No, but for 3 it does not work.
find the number of values of n for which it is possible to okay, so we have to find out the number of values of n. Oh, I see. I was thinking about the maximum value of n.
So the answer should be 75. I'm just trying to compute RBW for
The
n
answer
congruent.
should be 7. Okay, so there is an argument for this. Let's. Do you want me to come back to this, Arjun, for the n equal to 3 mod 4, or do you want me to wait a little bit?
Could you just wait for 1 minute if I'm not able to
Yeah,
get
yeah,
the answer?
yeah, yeah. Take your time. There is no problem. And then I'll be presenting problem number 21. Sorry, not 21. This is 20. Okay. This is. This is. This is 23. Or anyone has anything apart from these? Any other questions that you might have solved? Kunjan, Raghunath,
Maybe 26.
maybe 26? Okay. That's all right. You can think a little bit more about that. I think this was a very nice paper actually. Very nice paper.
Maybe you can proceed to some other question. I'll just try to finish
Yeah,
it.
yeah. Let me proceed to another question. This is problem number 23. And can someone put the problem number 23 on the board? Somehow I'm not able to upload the questions here. So can you just copy paste problem number 23 on the board? Someone. Okay. That's great. Thank you. Whoever did that. So let's look at problem number 23, friends. We are having the coordinate plane. Let's draw the coordinate plane, the xy plane. And the point is called the lattice point if both of its coordinates are integers. So both the coordinates are integers. And we have a point A here whose coordinate is 12, 84. 12, 84. So you want to find out the number of right angle triangles ABC in the coordinate plane where B and C are lattice points, having right angle at the vertex A, whose incenter is the origin. So origin O, this is the incenter. Now if you join OA, incenter means what? It means that OA will be bisecting angle A. OA bisects angle A. And we know that the triangle is a right triangle at the point A. So it must be like this. At the point A, maybe I can use a different color. The triangle must look like this. The question is it, why will it be parallel? Why would the red lines be parallel to the axis? Because we could have had something like this, right? Why can't we have maybe something like this? Can we have something like this? Maybe we can, right? Maybe the picture is, maybe the picture is like this. So this is 45 degree, this This is 45 degree because uh, it's a, it's it's angle bisector. So it's possible. It may not be true that the sides are perpendicular are parallel to the x and y axis. So now the question is, how many such triangles are possible? How many such triangles are possible? So we what we know is the other 2 points B and C are also lattice points. So maybe the coordinate of B is x1 y1, and maybe the coordinate of C is x2 y2. So
I actually have some problems with
yeah, go
that.
ahead.
So since O is the in center,
Right.
we know that it's the center of the in circle.
Yes.
Um, I'm not sure if that's a good circle. Yeah. So and we know that this oops, it will be perpendicular to the sides and the radius will be right.
Correct. Yes.
So and since these two tangents are equal, so this has to form a square.
This is a square. Yes.
Yeah. And we know that OA is equal to, by distance formula, it's just 12 square plus 84 square.
Right.
So that's actually 60 root 2. So we know that these sides of these squares are actually 60 because the diagonal is root 2 times the side.
So this is OA is 60 root 2. Yes. So the R is 60. Is that what you're saying?
Yeah.
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 R is 60. Correct. Because this is 60 root 2. Okay.
Maybe now we
So
can find AB. Okay, okay, go ahead. Yeah.
no, you got it. I was saying something.
Maybe we can find the equation of AB, like we have its slope, we know the inclination of OA, and we also know the inclination of AB with OA. So we can find the inclination of AB. So we have that inclination and one point that it is passing through. So AB equation we know, and the perpendicular distance to it is 60. So we can use that perpendicularity formula to talk more about the equation of AB and maybe the lattice points on that equation. That is coming to my mind.
So you were suggesting that uh, since this is 60 root 2, this is 60 root 2, this is 45, it's making an angle 45 degree with
Yeah.
this. So we can find the equation of this line AB.
Oh no, just a second. Like the uh yeah, I forgot that I can write. Just a
Yeah,
second.
yeah. Why don't you write?
So the slope of line OA is 4 because like 84 upon 12 will be
Right.
4. Oh,
That's what,
sorry. 84 upon 4 is not
it's not the slope.
4.
No, no, no.
Uh,
No, but what we can say is that this is 45 degree, right?
ha, ha. 7, 7. Yeah.
This is 45 degree and this is 60.
Oh,
This is 45
yeah.
and this is 60. The length of
Okay.
OT is 60.
Hmm. Yeah.
There is a unique line. So Arjun cannot hear anyone.
Oh,
Sorry.
yes, I can hear. I think maybe he should rejoin.
Yeah, okay. So this is 45, this is 60, and this we already know. This is tan inverse 4.
Hmm.
right?
7, sir, actually.
7. Oh, tan
Like
inverse 7. Sorry, 84 by 12, right? This is tan inverse 7. So we already know this angle, and we know this length 60. So we can probably find the
yeah.
we can find the uh,
Suppose this is theta, then tan of theta plus 45 is 7. So tan theta plus tan 45 by 1 minus tan theta into tan 45 is 7. M plus 1 equals 7 minus 7m. 8m is 6, so m is equal to 3 upon 4. I think that is correct. I just took it as theta, so and this is 45 degrees. So theta plus 45 is tan inverse 7. So
theta plus 45 is tan inverse 7.
tan inverse 7. So
Right.
so I got this. Then m is 3 by 4. Then y minus 84 by x minus 12 is 3 by 4.
Right.
So we just have to find the integral solution like a Diophantine equation. The integral solutions of these. How to find the integral solution? So 4y minus 4 fours are 16, 33 is equal to 3x minus 36.
Okay.
So 4y minus 3x is equal to 300. And the lattice points we have to see, there will be many solutions for this. And how to shortlist this.
All of these, I don't think will work
Sorry.
Yeah.
because
Can you?
all of these won't work because when we fix B, we kind of fix C as well. And we don't know for all values of these things, C will be a lattice point.
Oh, I see. So basically, the intersection of solutions of two Diophantine equations.
Yeah.
So we will find. So this corresponds to the line AB. Similarly, let's find the equation that corresponds to AC. AC will be like if it makes alpha, then tan of alpha minus 45 is 7. So 1 minus t by 1 plus t is equal to 7. So what will be t?
T will be, yeah.
7 plus 70. So 8t is equal to minus 6. So t is equal to minus 3 by 4. It's interesting. Minus 3 by 4 and this is plus 3 by 4. I think I did a mistake because the product should be minus 1, right?
Right.
Where did I do a mistake? Uh,
The, the other slope should be 4 by negative 4 by 3, right?
yeah.
Oh, it's done minus, so it should be. Oh, okay, that's right.
Alpha minus 45 is tan inverse 7. Oh, sorry. This is minus 7. Uh, Formula mistake. Yeah, t minus 1. So t minus 1. So we will get 60 is equal to minus 8. So yeah. Right. So minus 4 by 3. And that is correct because the product should be minus 1. Okay. Minus 4 by 3 means y minus 84 by x minus 12 is minus 4 by 3. So what will be the equation of, maybe I will go to the next page.
Okay.
So y minus 84 by x minus 12 is equal to minus 4 by 3. Then 3y minus 4 3s are 12, 8 4s, 8 3s are 24. 25 is minus 4x plus 48. So 3y plus 4x is equal to 240, 252 plus 48. Wow, 300. The same number. And here we have 4y minus 3x is equal to 300. This is corresponding to AB and this is corresponding to AC. Anyways, we just did not consider O as the incenter. We just have to find the intersection of the solution. I think
The
the
fact that
solution.
this might not work
Sorry?
because I don't think this works because we know that B is some point on this line and C is some point on this line. But it could be like this or like this. And we're not using that origin as the kind of like the
Oh,
incentive. So
yeah.
it probably won't work.
Bisecting the angle. Oh, now I can find BC equation, right? And we can put that condition. I have one idea. Let's see. So what is the solution of AB? I think it is like, what is the basis solution? 12 comma 84. So it should be 12 plus 12 plus 3k comma 84 minus 4k. This is like the general solution of a Diophantine like this. And for this it will be, say, k1, and this is 12 x means plus minus 4k2 comma 84 plus minus 3, so minus 3k k2. So this is point C, this is my point B. Now BC should be at a distance of 60 from the origin. I just have to find that thing. Will that be easier or will that be difficult?
So there is a distance formula from a point to a line, right?
Maybe we can equate that. I'm just thinking if there are.
Isn't there like only one way to do this? Maybe not. Okay.
Yeah, I think since it is asking for lattice points, we have to solve the Diophantine. So, anyways, we are going correct as far as I know. I think there are no space.
Okay. So
Should-
20. Oh, you move to 20,
Yeah.
and I can delete some of the initial ones.
Yeah. Maybe I will
Yeah.
sticky note. Is there a way to copy this equation and paste it in that board? Oh yeah, now it is free. Yeah. So B is 12
You're in,
plus 3. I'm in 16 right now.
yeah, yeah, yeah.
84 minus 4k1. C will be 12 minus 4k2, comma 84 minus 3k2. I think these are the solutions. Uh, I think like I did not make a mistake. Y is 84. So 84 minus 3, which means I have taken a plus and I have taken a minus here. And here x is 12, so I have taken a plus, and for y I have taken a minus. Okay, seems clear to me. So BC equation will be y minus uh, 84 minus 3k2 upon x minus 12 minus 4k2 is equal to difference of these two. So the difference of these two will be 3k2 minus 4k1 upon 4k2 minus 3k1. Sorry, plus 3k1. So this minus this, and then this minus this. Okay. Now if I cross multiply, I will get 4k2 plus 3k1 into y uh, plus 4k1 minus 3k2 into x, and then plus what will we get? And if I just substitute, I see I should get 60. Okay, so this will be important. So we will get, I'm on 17 now.
Okay.
So 4k2 plus 3k1 into 84 minus 3k2 plus 12 minus 4k2 4k1 minus 3k2 4k1 minus 3k2. So I think we should solve this maybe. 4k1 minus 3k2 12 minus 4. Yeah. If I solve this, oh, I think I can take uh, 3 outside to make the computations easier. So 3 into, I will get 3 2s are 6, 7, 8. 8 3s are 24. 28 minus k2. If I multiply these two, I will get so 8 4s are 32, 3, 4 2s are 8, 9, 10, 11. K2 minus 4 k2 square plus 8 3s are 24, 2, 3 2 are 6, 7, 8. K1 minus 3 k1 k2 plus, take 4 common, you will get 3 minus k2. So you will get 12 k1 minus 9 k2 minus 4 k1 k2 12 k1 minus 9 k2 minus 4 k1 k2 plus 3 k2 square. Right. So this will be 336k2 minus 36k2. So these two gets cancelled. Plus 4 3s are 12, 24, 25. 252k1. Then what is k1 here? 48k1. And then minus 16, minus 9, minus 25k1 k2. And then minus 12 plus 12 k2 square. So that will cancel out. Just funny. So this will be 300 k2 300 k2, and this will be 300 k1. Wow, they're simplifying to nice expressions. Plus 300 k1 minus 25 k1 k2. So this is the constant term that we have in the equation. 300 k1. So it will be like, oops, sorry. So this will be minus of, so 25 k1 k2 minus 300 k1 minus 300 k2 equal to 0. So the equation is, I will go to the 18th page. 4k2 plus 3k1 into y plus 4k1 minus 3k2. 4k1 minus 3k2 into x plus 25 k1 k2 minus 300 k1 minus 300 k2 equal to 0. The origin is at a distance of the in radius is 60, right?
Right.
So we just have to substitute the distance formula. The distance formula is like, first substitute this 0 comma 0 here. You will get mod of 25 k1 k2 minus 300 k1 minus 300 k2 divided by under root a square plus b square. So under root of this coefficient square plus this coefficient square. So that will be, just calculating, you will get 5 taken common, k1 square plus k2 square, right? Is 60. Yeah, times 2. Times 2. So now this 5 travels here and changes to 300. Okay.
I think just cancel the 20.
Sorry?
We cancel the 25.
25, yeah. K1, K2 minus 12, yeah. Minus 12 K1 minus 12 K2. The mod of this is equal to 12 root. This is computationally very heavy. K1 square plus K2 square. Okay, now 12 should divide K1 into K2. There are no constraints on K1 and K2. So that is there. Any integer would work. Okay, let us simplify this. So take K1 common. So, oh yeah, thank you. So take K1 common. It is K2 minus 12. And then take minus 12 common. It is K2 minus 12. And then you will have minus 144. And the mod of this is 12 root 2 into K1 square plus K2 square. So this is k1 minus 12 into k2 minus 12 minus 12 squared. This is equal to 12 times root of 2 into k1 square plus k2 square. Maybe we will divide everything by 12 because k1 and k2 must be divisible by. Oh, I think should each of them be divisible by 12? I think only the product has to be divisible by 12. k1 minus 12. How to even solve this? Maybe.
Maybe we can go back to what Arjun was saying and then come back to this one.
Hmm.
So Arjun, do you
Okay.
have a solution for that?
Huh?
You have the solution for the other case, right?
Yeah.
Yeah, let's go. Look, let's go to that. Yeah.
Uh, Actually, I found a much easier solution to the like not a much easier solution, but a more simpler solution to the whole problem. So I would like to present that.
Yeah, go ahead.
I want to. So which page can I use?
So let me just go ahead and delete the first few pages, and then you can use the starting point. Yeah. So let's go ahead and yeah. So you can start using page number 1.
Uh, Page number one. I think you mean 15, right?
Yeah, page number 15. Yeah, go ahead.
Okay, I'll start from 18 because Raghunath sir is doing that way. So okay, I think everyone remembers the problem. I'll just copy paste it once either way. Just a second,
Yeah.
or maybe I'll just move to the slide where Ashani sir had previously explained the problem. So I'm moving to slide number. Let me see. Slide number. I'm on slide number one.
Slide number 1. Okay.
Yeah. So I'll start from new. So essentially, we have a grid of such triangles as has drawn here, and we want to flip a set of triangles so that whenever we flip a triangle, we flip all three vertices of it, and we want that at the end of the day, every vertex is flipped exactly once. So the first observation we have to make is that the order in which we flip the triangles does not really matter. Like if you first flip this triangle one and then triangle two or triangle two and then triangle one, it doesn't matter. In a sense, this function is communicative and it's also easy to see it's associative. I mean, whatever that means. So the point is the order does not matter. And now another observation is that then there's no need to flip a triangle twice. Like if you flip a triangle twice, then that's literally doing nothing. So we can assume that every triangle gets flipped at most once. Now, I hope everyone knows the meaning of the problem. Now I'll go to page number 18 and write a very key claim. I'll write for so I'll write first this lemma and then I'll write a key claim lemma. There exists a set uh, X of triangles such that if I'm on page 18 by the way,
Yeah.
we flip everything in X, the the vertices in last four rows are uh, flipped, and every and everything else is same. So I hope the lemma is clear. Like I can flip a set of x of triangles such that it flips the vertices in the last four vertices and everything remains the same. So to explain the proof of this, I'll go back to slide number just a second, slide number 3. Uh, yeah. So essentially in this red set of vertices is acting like a required set, because uh, I mean, if you flip everything in this, like if you consider this set of triangles that I've drawn here, if you flip everything here, then all these vertices in these last four rows get flipped exactly once, and the other vertices are unaffected. Uh, Similarly, you can do this thing for n greater than equal to 4. N greater than equal to 4 here is important. It fails for n equal to 3. That's kind of something side case. So I had also previously proven this. And now I move to slide number 4. Here we are doing this the same thing for n equal to 6. If we select the set like this, then everything in these four rows is getting flipped, all vertices in these four rows, and while everything else above remains the same because we are literally just not touching everything else above. So the point of them getting flipped does not even arise. And how we chose this set is, I already explained that before. The pattern might be easy to notice just from a human's perspective, but what we do is, in the last row we pick all the triangles, in the second last row we pick the triangles alternately, and in this third last row we pick everything other than these two triangles on the leftmost and rightmost. So I won't explain more on that because I don't think mine explaining more will help, but actually what will help if you people try to observe it yourselves more. So I hope the lemma I have written on page 18 is clear. Now I'll move to page 19 and write another lemma. Oh, sorry, our key claim. Key claim.
Okay.
So my claim is n works if and only if n plus 4 works. So let me try to prove this claim. So first I'll assume that n works and prove n plus 4 works. Then I'll assume n plus 4 works and prove n will also work. So assume n works. So this is exactly the induction we did previously. If we if we have this set x of triangles such that everything in the bottommost four rows can get flipped. So if I consider a n plus 4 triangle, I first cover the n vertices above by operating in that triangle, and then I can cover the below vertices by flipping everything in x. uh, does that make sense, or is it a little vague?
It makes sense, yeah.
And now conversely, if I assume that n plus 4 works, and if I flip everything in the set X, then everything in the bottom, all vertices of the bottom four rows become head again, and everything above is just tails. Wait a second. Uh, Actually, I'm sorry, this might fail. Yeah, yeah, maybe we can go to some other question. I'll try to fix this again.
Okay. Okay, no problem. Let me go ahead and try the problem number 20. So can someone put the problem number 20 on the board? Problem number 20. I don't know why it is not allowing me to put the questions on the board. Okay, thank you. So problem number 20 is very nice actually. So it says that any finite set of uh, for any finite set x of integers, let max x denote the largest element of x and mod x denote the number of elements in x. If n is the number of ordered pairs A and B of finite non-empty sets of positive integers, such that max A times B is 12 and A times max B is 11, then and n can be written as 100A plus B, where A, B are positive integers less than 100, and find A plus B. So let's look at this problem. So we know max A times mod B is 12, which means mod B is equal to, so what are the possibilities? Mod B is equals to 1, max A is equals to 12, mod B is equals to 2, max A is equals to 6, mod B is equals to 3, max A is equals to 4, mod B is equals to 4, max A is equals to 3, mod B is equals to 6, max A is equals to 2, and mod B equals to 12, then max A is equals to 1. Okay, so these are finite set of non-empty set of integers. Okay, all right. So the other condition, so this should simultaneously follow, is that mod A times max B is equals to 11. Now this is much easier. This means mod A is equals to 1, max B is equals to 11, and mod A is equals to 11, max B equals to 1. Okay, so we want both of these situations to simultaneously satisfy. So there are 12 cases, 12 such case subcases. So maybe I can, I don't know, write each of them and check. So basically, let's look at the first case. Mod A equals to 1, max B equals to 11, mod B equals to 1, max A equals to 12. This means A is equal to the set of 12 and B is equals to the set of 11. So you have this situation. So this is one case. Now the second case is mod A equals to 11 max. So we have mod A equals to 1, max A equals to 6, mod B equals to 2, max B equals to 11. So there are two elements here. Maximum of it is 11. How many are, so these are positive integers, non-empty set of positive integers. So the possibilities for B are 1 to 10 sets, so cannot repeat. So there are 10 of them, 10 cases here, one case here. Okay. The next one is mod A equals to 1, so this is 4, and B has three numbers. The largest one is 11. So the remaining two numbers must be chosen from 10. So there are 10 choose 2 cases. Similarly, here mod A equals to, so A is equals to 3, B equals to, there are 3 slots and 11, so 4 things, 4 items. So I have to choose these 3 numbers from 1 to 10. So 10 choose 3 cases. And then similarly, this you can see what's going on. So here this one will be 10 choose 5 cases. 6 of them maximum value is 11. So 10 choose 5 cases. And 12 of them maximum value is 11. Now that's not possible. So this last one will not work, not happen. That is max B is 11, but the number of elements in B is 12. That's not possible. So we have 10 choose 1, that is 10, plus 10 choose 2. 10 choose 2 is 10 times 9 by 2, that is 45. 10 choose 3, 4, 3, actually 120. And 10 choose 5, 10 choose 5 is 10 into 9 into 8 into 7 into 6 by 5 into 3 into 2 into 4 into 3 into 2 into 1. So 4, 2, 8 cancels off, 3, 2 cancels off, 5, 2 cancels off. So we have 2 times. So okay, so maybe I can just do the calculation. Yeah. So 10 choose 5. That's 252. Okay. So that's the first case where the max A is 1. So we have total 10 plus 45 plus 120 plus 252. 10 plus 45 plus 120 plus 252. That is total 427 cases. This is when mod A is equals to 1. So what happens if mod A is equals to 11, max B is equals to 1. So if max B is 1, none of these, so none of these 5 cases would work. Because if max B is 1, that means the largest number in B is 1, and it's set of positive numbers, distinct positive elements. So it cannot have more than 1 element. So all of these cases are gone. It can't work. So the only case is this, that max B is 1 means B is equal to 1, and A has 11 elements and max A is 12. Okay, so you have to basically check the remaining 10 elements. There are 11 elements, the 11th one must be 12. The remaining 10 elements, so in 11 choose 10 ways. So there are 11 such cases. Now that means we have precisely 11 such cases, so plus 11, so 437 if I'm not wrong. Maybe there is something repeating. Let me double check that. B contains only 1. No, I don't think that is happening. Okay, that's great. So I think this is fine. 437.
Sir, is the answer 437 or?
The answer is not 437 because the question asks that n can be written as
Okay.
100A plus B.
Oh, I see.
So 437. So this is N is 100A plus B. So now this is a bit confusing for me because A and B are positive integers less than 100. So for example, A can be 4, B can be 37.
Yes, that is the.
That is possible. What else is something else is possible?
Sir, no, sir. Like there is a unique remainder mod 100, right?
About
So
100 there is a unique remainder, so it's not possible.
37.
So we want it, so that's 41. So the answer is A plus B is 41. Did
41.
anyone get 41 for number 20? For the people who are watching, for number 20, did any of you get 41? If my calculation is not right, I don't know, I have to check. So, yeah,
Sir, 23. I got 18. The lattice point.
the lattice point
Uh,
thing you got it? Okay.
yeah, yeah, yeah.
So,
So basically,
yeah,
oh, I will.
23, the answer is 18. Okay.
So the same procedure only. Like instead of going into the distance from origin,
Uh huh.
we will go through the angle BIC. Angle BIC is 135 degrees. So
So,
I'm in slide 11.
slide 11. Okay, let's
Yeah.
go to slide 11 now. Okay.
So now
Yeah.
we know that points B and C will lie on this line AB and AC for all integers k1 and k2. So we just have to find the integers k1 and k2. So instead of equation of BC, we will take this. I
Okay.
don't know how
Sorry for interrupting. I think the last step in the calculation I made an error.
Oh, okay, okay. Yeah, yeah, yeah.
Yeah,
You can go to that
yeah,
slide.
yeah. I think I made an error. 1 second. Let me double check.
Hmm.
So, oh yeah, yeah, yeah. This is 438.
Oh,
Okay, let's see. 438. Even then, I'm getting 4 plus 38. How are you guys getting 43? Some people here got 43. Isn't it then 42? Because A is 4, B is 38. How is it coming 43? I don't know. Some people are saying it's 43, but 427. Maybe I made an error in adding. Let's see. Oh, I made an error in adding. I missed one case. Oh, okay, one. Yeah, 439. Got it. So now it's fine. I missed the first case when A is 12 and B is 12. Okay, so now the answer is 4 plus 39, that's 43. 4 plus 39, that's 43. Correct. Thank you, guys. Okay, let's go ahead and go to number 17. Yeah. Oh,
Also, sir, if possible, on the last page, can we like make a table and write the answers to all questions we are getting?
yeah,
For
yeah, yeah.
the-
I'm already making the table actually.
Oh, okay, okay.
I am planning to post it as soon as it's all done. Yeah.
hmm. So yeah. Is it visible?
Yeah, it is visible.
Okay, okay, okay. So we know that BIC makes like 90 plus A by 2, right?
Right.
Because this is B by 2 and this is C by 2. So this is 90 plus A by 2 in any triangle. And A is 90 here. So this one will be 135 degrees. BIC. And basically the incenter is origin. So, and B is of this form and C is of this form. So let's use the slope formula, that is tan of theta 1 minus theta 2 is equal to the slope of IC. Let's take this slope is m1. So basically in the thing you have IC to be like this. This is your angle theta 1.
Mhm.
B is here. This is your angle theta 2. So theta 1 minus theta 2 will be the middle angle, 135 degrees, the BIC angle. Because the configuration is just fixed in the plane. So the BNC must be here only. Like this is a ray AB. So BNC must be like this only. So the configuration is like this. So it is 135, which is tan of like theta 1 minus theta 2 is 135. Tan 135 is minus 1. But we will find it in terms of slope separately. In the sense, it is equal to the slope of OC. Say MC is the slope of OC. MC minus MB by 1 plus MC into MB, right? So we will get uh, MC minus MB is equal to minus 1 minus MC MB. This is what we will get. And this is what MC into MB plus 1, and here you have MB minus 1. Oh, okay. So anyways, so here we have MC minus MB is minus 1 minus this. So this, I got it to be, oh, page 12 I will erase.
You're in
I'm
page
in
12?
page 12.
Okay.
Yeah.
Okay, got it. So
So the la
should I delete everything here?
I have erased everything, sir, in page 12.
Oh, okay.
Is there a way to delete the page directly,
I
like the content?
Yeah, I think there should be.
Okay, okay. So let's write this. We have MC minus MB is equal to minus 1 minus MC MB. So the MC MB values are like taken from this. So this y coordinate divided by the x coordinate is basically MC, right? The slope of line IC will be this y coordinate by this x coordinate, because I is the origin. Now we will divide them. You will get 3 by 4 into, I think you will get 3 common. You can take 3 and 4 common from numerator and denominator respectively to get 28 minus k2 upon 3 minus k2 minus 4 by 3 into 21 minus k1 by 4 plus k1 is equal to minus 1 minus this 3 by 4 and 4 by 3 gets cancelled, and you will have 28 minus k2 by 3 minus k2 into 21 minus k1 by 4 plus k1, right? Now this will be just writing after simplification. So 12 into 600 minus 25 k1 minus 25 k2 is equal to 16 into 63 minus 3 k1 minus 21 k2 plus k1 k2 minus 9 into 112 minus 4 k2 plus 28 k1 minus k1 k2. Just taking the LCM and cancelling 3 minus k2 into 4 plus k1 both sides. You will get this. And now I just simplified myself, but it is little bit lengthier. After simplification, you will directly get this. K1 k2 is equal to 288. This is what we will get.
Oh,
It simplifies to this.
wow.
So this I'm unable to understand why it is so simply like simplifying. That is like a magic. So now this is 2 power 5 into 3 square. So basically number of integers k1 k2. K1 k2 can be negative also. That is fine. So tau of k1 k2 will be counting the positive devices like 6 into 3, 18. I just forgot that there are also negative devices. So it will be number of values of k1 will be um, not 18, like negatives of that, which will be 36. Similarly, you will get k2 because 288 by k1 will be k2. So 36 will be the number of triangles because for each k1, like in the page, the 11th page, you could see that point B is defined. And similarly, we know that k2 is 288 by k1. So the value k2 is like C is defined by k2. So that means like 36 triangles are possible. That will be the answer.
36. This number 26 we are saying as 36.
23.
23. Oh, okay.
Yeah, yeah, yeah.
23 is 36. Okay.
Yeah, yeah,
So
yeah.
I think this is going on for a very long time.
Yeah, so I also have to leave now.
Yeah. But
So,
let's go to last thing. Let me ask Arjun, do we have something for the last one, the one that you were trying?
Yeah, I'm done on 29
It
and
was
hopefully
29.
correct this time.
Yeah, what is the answer that you're getting?
I'm getting the answer as 67.
67. Okay.
Let me just verify if it's 67 or 33. What did they ask in the question?
For 29, it's asking the yeah, 29, right? No, is
Yeah,
it
yeah. For
29?
oh, it's 28, and for 28, it's 67. Yeah, 67.
67. Okay. 95, 28, it's 67. Okay, so can do we know why? Like, do you have a do you want me to get to a particular board?
Yeah. First, I'll get to board number 3 and tell why my previous arguments were wrong.
Okay.
Board number 4. Sorry, board number 4.
Raghunath, if you want, you can leave because after this we will be shutting down. Yeah. Okay. Thank you.
Sir, if possible, can I continue the meet even after this?
Sure.
Yeah. Yeah. So in number 4, yeah. So what we were previous, I said that in this construction of red triangles, everything in these four rows are getting covered an odd number of times. But if we look at this one, this thing, then it is getting covered an even number of times. So that's where my argument fails.
Mhm.
So essentially, 2 does not imply it works for 6, and the answer is it works only if n is 1 or 2 mod 3. So I will present and I will start from literally I will start from scratch. So can I
Yeah, so let me just do one thing. Let me delete all the boards because to,
just don't delete 1 and 2.
I will not delete one and two. I'll just leave one, two, three, four, maybe.
Yeah, you can delete anything you want. I'll either way start from scratch.
Okay, so let's delete everything else. Okay, so I think you are in board six.
Yeah.
Okay, so here we go.
So I'll again define how are we coloring. So
Yeah,
we
you continue. I'll be back in a moment. Okay.
yeah. Uh, so we color like this. So I've already defined it previously, but I'm telling it again. So just to give a quick review, so we are coloring it like this, and other colors go like this: blue, blue, and the last color is, this is how we are coloring the vertices. Uh, okay, so essentially, so I'll define more formally how we color the vertices. So if I consider this as the x-axis, this as the y-axis, and this as the z-axis, and I already mentioned how we can label every point as some pair x, y, z, where x plus y plus z is equal to n, and they are all non-negative. Uh, so essentially, uh, so this point is, for example, 0, 0, n. Uh, okay, and this point is like 0, 1, n minus 1. This point is then like 1, 0, n minus 1, and so on. So uh, if x minus y is congruent to 3, 0, I'm working modulo 3, then color red, mod 3 I'll just write here. And if x minus y is congruent to 1, color yellow. And if x minus y is congruent to 2, you color blue. So, okay, one observation, I'll make several observations. Okay, the first is each triangle. In each triangle, uh, we have exactly like one vertex of each color. And the second observation is if I consider any such line like this, then in each such a like line of three consecutive, I have exactly one of each color. This is not very hard to prove by this formal definition, or maybe you could just use this fact and like prove it. Like it's not really that hard. Yeah. So we have gotten that in each triangle we have one of each color, and in each such of these three, in a line in a three we have one of each color, and there are three types of lines, and I marked all of them in this figure. So now I go on to Jamboard 7. Mm, yeah. So let x denote the number of them which are red. Let y be the let y be the number of them which were like blue, and z be the number of them which were like yellow. So even let me use x and y and z. And so my claim there exists uh, some constant lambda n such that x of n plus 3 is equal to xn plus lambda n, y of n plus 3 is equal to yn plus lambda n, and z of n plus 3 is equal to zn plus lambda n. And I will prove this essentially whenever you go from n to n plus 3, all of x, y, z get increased by the same constant. So for the proof of this, let me go on to Jamboard number 8, and this time I'll put another figure. Essentially, I'm trying to prove that. Yeah, let me just first put the figure, then it will be clear what I'm trying to prove. So yeah. So suppose so I have this big triangle, and I am extending it by three lines, and I want to prove in this subsection uh, there are our claim is equivalent to proving that in these three rows the number of red, the number of yellow, and the number of blue are like same. So what you can notice is in these diagonal lines all of them are equal. and then in this small triangle all of them are equal. So here I have exactly one red, here one red, in this line one red, one red, so all of them are equal. So I think the lemma I have proven, the claim on page 7 is proven. I won't go in more detail of this because I hope, because like this is there is a lot to the problem and we can't just stop here. But I think if you think about this a little more yourself, you will find everything is quite natural. So now I'm on page 9. So I also proved that we must have, suppose there is a valid finite number of moves, then xn congruent to yn congruent to zn, number of congruent to number of moves, mod 2. I had already proved it previously, and I'm not proving it again. You people might be able to prove this quite easily yourself. Here we are using the property 1, that each triangle has one of each. Okay, so yeah, we are using this property. So okay, now let's see how does the, also I'll define for n equal to 0. For convention, for n equal to 0, I just consider this dot as the vertex, any the dot as the grid. So okay, for I'll now I'm on page 10 and I'll make a grid. So and this is mod 3, n congruent to 1, n congruent to 2. So okay, and this is a x, y, and z. So it is easy to observe that for n equal to 1, I have 1x, 0y, and 0z. And in general, when n is congruent to 0 mod 3, I have x as some 1 plus alpha, y as some 0 plus alpha, and z as some 0 plus alpha because of the lemma. Like, yeah, when I increase it by 3, all of them get increased by the same constant. Again, I'll not spend a lot of time on this because you people might be able to observe this. Yeah. And for n congruent to 1, I have this as like this is 1. So this is like some 1 plus beta. This is like some 1 plus beta. This is like some 1 plus beta because in n equal to 1, I have 1 1. So this is like n equal to 0. This is n equal to 1. And this is like n equal to 2. Okay. And this is then like 2 plus gamma, some 2 plus gamma, and 2 plus gamma. Okay, so we got that for some n to work, we must have x, y, z same parity, right? So it's clear that n congruent to 0 fail, right? Only n congruent to 1 and 2 might work from our observation. Like we know the number of x, number of y, number of z must have the same parity, and from our observation, uh, only n congruent to 1 and 2 can work. This also motivates, so n congruent to 0 fail, and this is also motivating us to conjecture that n congruent to 1 and n congruent to 2 will indeed work. So next we try to prove n congruent to 1 mod 3 and n congruent to 2 mod 3 work. Now in such type of questions, when we are to prove say like n congruent to 1 and n congruent to 3, n congruent to 2 mod 3 work, it's natural to try induction in steps of 2. Um, what I'll say now might be a spoiler for people who haven't tried InMo 2021 problem 2. Uh, oh, sorry, InMo 2022 problem 2. But maybe those people can just close their ears. So in InMo 2022 problem 2, uh, we had a similar thing where uh, regarding modulo 3 we had some condition of working and non-working, so we did induction in steps of 3. So here we'll do the same. So I move on to page 11 now. So essentially what I'll now prove is that if n works, then so does n plus 3. And since it is quite easy to see that n equal to 1 and 2 work, so I'll just tell why n equal to 1 works, you just operate on this triangle, and why n equal to 2 works, you just operate on these corner triangles. So no, you literally operate on just everything. So okay, now I will move on to the induction step. Essentially, what I'll do is that I'll assume it like uh, just a second. I'll assume it works for n and I'll prove it that it works for n plus 3. So we have this triangle back again. So uh, so just a second. So suppose we have already filled up this triangle, okay? This triangle, this shaded triangle. Suppose we have already operated here in the triangle such that this works. Uh, Sorry, let me go back. These things won't be there. These things won't be there. So let me color it more properly. So I have this triangle, and I have already operated in this triangle. Now I want to focus on these three last rows. So how I operate on them is as follows. I literally pick up everything in the last row, and I pick up alternately in the above row. Now it is not hard to see that everything in the bottom here, like everything here in these every vertex in these last three rows get operated like an odd number of times. And this is how it works. Another observation is that the triangles we are operating below does not affect the this big triangle up here. So the unit triangles we are operating below does not affect the above one. For example, had we say operated this triangle, then that's not fine because then even this vertex get affected. So we can't do stuff like that. So this works and this completes the induction in a sense. So I think I have included all the necessary details you won't need to solve this question. I agree that it might be hard to grasp this solution as the problem is actually hard. So I won't go into more detail because I've already talked a lot. And if you want to understand this more clearly, I think if you just try to understand what is happening here and spend some time on it own, you will be able to understand. And yeah, nothing much to say. Just try to uh, follow the argument or just try to see what's happening and you'll be able to verify everything and you'll be easily convinced that the solution works. Now I'll tell some few comments on the problem. I'm again commenting that in my view this problem is really hard. I think this is INMO level easily. This is not PRMO level. This is easily INMO level. So probably in a test it's a good idea to skip this question or whatever. Or maybe after getting one to work and three fails, you can conjecture modulo three something is happening. I don't know. But overall, let me conclude to the answer of this question. So we were looking at numbers 1 to 100 and we know only multiples of 3 fail. So the answer is 100 minus 33 which is equal to 67. So the answer of question 28 is 67.
Okay.
Yeah.
Yep. Okay, this one is quite challenging. Quite challenging. I wonder that if there is a easier way to. So I see the induction argument that you are making, which is if it works for a number, then it works for the number plus three, right?
Yeah.
Yeah. So why? So maybe we can think later more about this. Maybe there is a way to directly deduce that it wouldn't work for any other stuff. Okay, so let's try another one. Which one do you have anyone in mind that you would?
Uh, I don't have anyone in mind right now, but I if you have, you can continue. Yeah.
Okay. Let me just continue. let me. I think I will try problem number 15 on the board. Though I have not studied the problem at all, but let's see if we can do it. So 15, problem number 15. So here is problem number 15. It says that ABCD is a unit square. This is problem number 15. Problem 15. It says that ABCD is a unit square. Unit square means its side lengths are 1, and it's given that M and N are points on BC and CD respectively. M is on BC and N is on CD, such that the perimeter of the triangle MCN, so MCN is a triangle MCN, perimeter is given to be 2. So the side length of this square is 1. It's a unit square. And the perimeter of the triangle MCN is 2. Let O be the circumcenter of the triangle MAN. So you join NA, you join MA. Okay. And you draw the circumcenter of the triangle MAN. So that means you take the perpendicular bisectors of the three sides, and wherever they meet, that is the point O, which is the circumcenter of MAN. And we have the circumcenter of MON. So MON, let's draw MON. Of course, MON is an isosceles triangle because OM is equal to ON. Again, we draw the perpendicular bisectors of the three sides. So one of them is this one. So it's possible if it's an obtuse angle, whatever this angle is, this one is double of that. So if this is more than 45, then this is an obtuse angle. In that case, it's possible that it goes outside. So anyway, you draw the circumcenter. So P is the circumcenter of triangle MON. P is the circumcenter of triangle MON. Okay. So this is the next one. Okay. So what we want to show, what we want to find out is, so our goal is to find out OP over P is the circumcenter. So here is P, suppose. OP over OA whole square. Suppose this is M by N, where M by N is relatively prime. GCD of M by N is 1, M and N is 1. So you have to find out the value of M plus N. So how do we go for this one? So this is OA.